So it's my pleasure to open this session entitled Metal Coloration by Photonic Processes. The first presentation will be given by Sedao and me. So Sedao is a research engineer at Laboratoire Berthurien, and he also works on surface texturation, mainly with ultra-fast lasers. And we will present this course on pulse laser for direct colorations of metals.
So let's get started. I just recalled the title again, is pulsed laser for direct coloration of metals. Then before we start, I just want to share a gallery of realizations samples we made by laser engraving, laser marking, either by realizing the different shades of grease or by rendering a surface with different colors. And so for this page of gallery, this is all the samples we made in our campus by ourselves or by our colleagues in the Institute d'Optique Graduate School, Telecom Santiago, Manutech-SLEIGHT, all people from the US Korean country. So that's just an example of ideas what we do with our lasers. And then this is really the structuring of this workshop in the afternoon. First of all, I will be giving a brief introduction on laser material interaction. And then it's going to be Florent. He will be speaking a bit of overview of color appearance on metallic surfaces, the different pathways of getting a color on the surface. With this part two, with lasers, with surface colors, and then we can go through a couple of case studies, a couple of examples of how we do the surface colors and how we use laser-related laser processes, laser parameters, and so on and so forth. Then towards the end, a very quick conclusion, some messages to take home. Now, first of all, I will be talking laser material interaction. At the very beginning, it's a technical issue. That I have a laser spot, right? I have a laser light. It's very small. So how do I do a large surface areas? In order to do that, we need some tools. It's called a laser scanner, a cartoon showing a schematic, showing the mechanism of laser scanning. You have your laser beam coming in, and then you have a pair of motorized mirrors. So one mirror sweeping this way to deflect laser lights in y-axis, and then the following one deflect laser lights y-axis. The combination of the two then give you a laser scanning in a two-dimensional space that realized in a large surface area. So redo demonstration. Just that's our laser scanning there. And you're seeing a green bar. In fact, it's a laser spot. It's a point source. You can see it's highest. And the reason for which you see a line, because laser scanning so fast and our eye just can't catch the movement. So in the end, you feel there's a line. In fact, this is a laser scanning by those motorized mirrors, then to realize a big surface area of its. Once it's done, you can see this is some rows perspectives, different breeds of shades of grays. And then the second page is to do with scientific part aspects of laser material interaction. Then what is happening when I have a laser shines on a metallic surface? I kind of personally is not pure something. I just categorize them into three different families. They are in three different boxes. The first one is continuous laser. Continuous laser is good for heating a material, bringing the material temperature to fusion. And then this is good for welding, for joining, for additive manufacturing, for example. This is normally micrometer scale, and this is not really what we are interested of today. And then what we are interested in third boxes, where we have a pulse lasers. We see a box in the middle is called short laser pulses, and this kind of is like laser flashes. Each flash taking a time window, a nanosecond duration time window. Nanosecond is a small portion of a second. It's 10 to the power of minus 12 seconds. It's small, it's short, but it's not the shortest. We get to that later. Just to say a nanosecond of short laser pulses, they are very good for heating a material, but in a very small volume. As a consequence, you can bring the temperature to melting and bring the temperature to evaporation and to remove material from the substrate, for example. And then as well in the vicinity, you have high rise of the temperature, which is good for a certain surface chemistry reaction. That we'll come back to this point as well a little bit later. Then towards the last box there, you have this ultra fast, ultra short laser pulses. This is again 1,000 times shorter than nanosecond than short laser pulses. It's very, very short, 10 to the power of minus 15 seconds. And this interaction is quite different from what I have been talking. Like in the ultra short regime, you have just laser photons interact with the electrons of the surface, and then they're no longer lasers. What's happening afterwards is the energy, is the electron transferring the photon energy into the atoms, and then atoms may leave the surface, a big explosion, and so on and so forth. And by this, there's no heat transfer involved. As a consequence, you can have a very precise laser micro nano processing. Here, two showcases that do engraving on a mesh board and drilling a hole on the human hair. So the second part should be colors.
Yes, before going into what we create as colors with lasers, we just wanted to show you two ideas of how we obtain colors. So this morning, Mr. Simono described to us how colors emerge from optical constant of metals, but there's actually a second way to have colors, so what we call structural colors. So structural colors actually come from a different scale of interaction. They arise from the indexed structuring of the material and from interferences. So this is what happens when you have, for example, diffraction grating, where the light will be dispersed, diffracted by small organized structuration. That's what happens very well used in Bragg in optical fiber, where Bragg grating can reflect a single wavelength based on this organization. This is also observed in thin films. There are conditions when the light will go through a thin film, and we will describe it more clearly later. When the light goes through thin films, some of the light can get out of the film with interferences too, constructive or destructive interferences, and then so the size of these structures should be close in the order, let's say, of the wavelength of the laser or higher, and we will observe a strong angular dependency, so support iridescent colors. Just to say that, for example, what you have on the sub level. To take a more accurate example, people love to talk about biomimetics, so let's do it also. An example of structural color is the morpho butterfly, which has this beautiful blue and brilliant coloration. When you look, if you just crush it and extract the wing material, it is transparent. It will be white. But it is organized, you look with the SEM, scanning electron microscope, into some kind of fiber grating. To say some lamella here that you see that are periodically arranged. So that will act as a diffraction grating and send the light back in an organized way. So we have this strong and iridescent blue, and obviously if you tilt the light coming to the wing, you will have different wavelengths for the constructive or destructive interferences that you need. And so you will have different colors if you see different colors. So this is what we call structural colors. And which will have a very huge importance in the rest of the talk. Obviously, the other way is what I described. It's what I call here pigments. The color is due to the electronic structure of the material. So to go on, nature also found this idea to color the butterflies. They have different organic species in their wings that absorb light in different ways. That's how they obtain. Can we have pigments when we have metals? We saw this morning that metals have very, very general flat reflectance, or some of them are colored gold. But what actually has very different colors is oxides. Actually, metal oxides are used as pigments in many, many conditions. Here you have TiO2, which is a very classical white pigment we will have in plastics, some painting, some paint. Here you have nickel oxide and tin oxides, like this, I don't know. Here you have iron oxides, which are the red hues, some hydrogenated. Here you have this compound of titanium, zinc, etc., which is green, and you can find all of them. So actually, if we manage with our laser to oxidize metal, we will manage to have a lot of different colors. So now we will start with the results obtained with structure.
So next one, let's start from that is what's called topography induced color. We start from something very dark and intensive black. And this is kind of first an example, simple example. Let's imagine together the basketball. On the basketball, you have a true hole where you can pump air pressure inside speaker. And imagine that we have one light ray goes in that hole, goes into inside of the basketball. Then what heat? That he's in the first position, and then there's reflection. And then the reflected light hits to a second position, you have a second reflection, and third, fourth, fifth, and so on and so forth. The fact that this true hole on the shell of basketball is very small. So in reality, it's just not possible for the light rays to go back in the vacuum to the external world. And that's why when we look at this entrance, it's pure black. It's just because there's no light emission whatsoever. And that's is about the sphere. And then we can do that on the planar surface as well. To do an analogy, that we have a landscape where we have flat views, and then it's always darker in the forest. And then we can engineer these concepts on our surfaces, metallic surfaces. We do that in a micrometer scale, of course. This is a representative of surface multi-scale surface topography in micrometer scale. You have this in micrometer. They are micrometer forest if you want trees. On the scheme on the top of the trees, there's second scale, smaller branches, twigs, leaves, and so on and so forth. They are nanoscales. And the combination of these multiple scale structures, hierarchical structures, ensures that the light is coming in, they get reflection, multiple reflection events, and the reflection only go deep up downwards, and there's no back reflection. So overall, the perception appearance is black. This is the design, and this is the realization. Because we need to do those multiple scale structures, we use our ultra short laser pulses to gain this ultimate machining precision. We create micrometer scale bombs. This is a top view, for example, in a square, a bomb of 10 micrometer in dimension. And then if we zoom in this square, we can see that each individual bomb they covered many 100 nanometer round peaks on bombs. And then if we can even further this highlighted by a yellow square, and if we see in the yellow square, zoom in again, then you can see the 10 nanometer scale of nanoparticles. It's the combination of all this stuff making the surface black, as we will show. First of all, this is our reference curve. As this is a stainless steel over the spectrum range, visible light spectrum range from 400 to 800 nanometers. When it's a metallic surface without any treatment has received addition, we have a 40% of reflectance or the light reflection after the light shining on the surface. Whereas for these our microforest multi-scale micrometer scale structures, laser pattern stainless surfaces, then we have a reduced reflection. Reflectance lower than 2%, as is measured here and represents this graph. And it's not only, as we can see, not only visible range, it extends to near infrared as well. But there are potential applications there. And then maybe at this moment, I have some questions. That's how did you know to produce those hierarchical multi-scale surface structures with lasers? And well, that's because we have been working in this for many years. Here is a small representation of all things that we know to produce. We have, for example, this is the one of a hierarchical microforest, and we know more like grooves, like big scale nano periodic structures and small scale small nanoscale periodic structures. Small, and that's leading to the next session.
So if we go to the next, yes, if we focus a bit, so Sedao just show you the results that we could obtain with the spikes. Obtain with the spikes here. If you change a bit your parameters, your laser parameters, when you with the surface, you can have all this range of structures. I want to insist on this. This was something that will appear on almost all materials if you go with a femtosecond laser and try to hit them. It will work on almost all metals. This kind of structure spikes, grooves, LSFL, HSFLs, you will find them all the times. This is very basic setup, as Sedao showed. You just scan the surface, no interferometric setup necessary, and you have all these well-organized structures. So there are lots of different structures that we classify with their periodicity. So there is small ones, much smaller than the wavelength here. The nanoscale, sorry, on the right inside of this image. So high spatial frequency beeps, these are induced periodic surface structures, or even 2D study. And in our case, mostly we will look at this LSFLs for the coloration of metals. That's what our people are doing. Some of them are also doing this kind of double with several directions, but very well organized. And if you look, for example, now with the developments of scanners, lasers with high repeatability, you can almost have perfect ratings with periodicity in the few hundreds of nanometers. So here is an example, like this paper, they found the best material to be molybdenum, but they also have very good structures in steel. So what happens if you have a periodic surface? Well, why do we have this periodic surface? There are several explanations. This has been a very debated subject for 10, 15 years. Now we kind of have, for the low spatial frequency beeps, a clear explanation. When the laser first impinges on the surface, it will be diffracted partly by scattered by the roughness of the surface. This scattering creates interferences on the surface, and these interferences are enough to create a periodic distribution of energy, periodic inhomogeneity in the distribution of energy. When they will interfere with the purpose. And then there are some feedback effects that will take place as another pulse comes to the laser and interacts with the first modifications that we have done. And pulse by pulse, we'll start to obtain more and more regular structures. So we don't go into detail, but the feedback from the feedback effect here is between the precedently irradiated matter and the next imaging pulse. And it is amplifying effect of the periodicity. It has been suggested a lot that some specific waves that can arise, which are called the surface plasmons, can enhance this phenomena because they are electromagnetic waves that will appear on periodic surfaces. Sorry. Okay. For the other ones, we don't have a very clear origin, so I will not go into detail. They have been hypothesized to come from EFA scattering, from hydrodynamic instabilities. A lot of things exist, and you've seen we have a lot of different regions. So, to the point of coloration. If you have a grating and you send light on it, part of the light will be directly reflected. This is what we call the zero order of diffraction. But diffraction leads to having, when you have a periodic surface, this formula. This is to say that the refracted order is linked to the ratio of the light periodicity to the grating periodicity, big lambda. And so you will have dispersion of light in two directions here, for example, for the first and minus one and minus one order. And you can have even more orders of diffraction with this figure n. So this is ratings that are using spectrometers using this kind of periodicity. So here, example of everything with periodicity larger than the wavelength. So where you will see many colors appearing. In the case of lips, you are much closer to the wavelength. So in general, you have only a few orders that are different. And so this is the occasion to ask Jeanne, who so Sedao, people from Manutech, Jeanne worked on making structures last week. And so she will pass around here the first structures that we obtain, which consist of lips. And after we will pass other samples. So the first nice experiment that was on lips, here you can see is coloration of aluminium. So this is a sample of aluminium seen from different angles. You see that here at the 25 degrees or something, you see green, and as you change, some kind of purple, and then some kind of yellow. And it all comes from this structuration of the surface. So this is a sample that will pass around. And to complete, here is an example of a very nice work that has been done combining ultra-short pulses with the scattering technique and an optical parametric amplifier for selecting the wavelength of our lasers. And you can see that we obtain all kinds of periodicity. And as you do that, you can see here all the different colors that were obtained from these lips in the various surface fringes. So here, you can see it's different. In the vertical, you have the periodicity, and in the horizontal, you have the angle from which they are seen. You see that we can go from the blue to the orange, and so on. So this is how to obtain a full range of iridescent colors on, for example, stainless steel. The question is that, can we use the lasers to have non-iridescent color? What I showed for now is ultra-fast lasers creating surfaces. But the other way is to have oxidation. So most metals, as you know, will oxidize. You have the Ellingham diagram of all metals. So the way to read this is that on the vertical axis, you have the free energy of the oxidizing reaction of metals, and here you have the temperature. And you see that all metals here is magnesium, this is aluminium, titanium, and so on. They all will want to oxidize in ambient temperature. Of course, that's one thing that they are more or less stable on some sides, and the kinetics they rely on. So what are the kinetics of metal oxidations? Here, for example, you can look at nickel oxide oxidizing. There are several regimes. The first one, so this is the growth rate here of the oxide thickness. And so it starts very fast, slows down from the so-called Cabrera-Mott regime to the Wagner regime. You have the different scale, less than 10 nanometers per Cabrera-Mott, and more than 100 for Wagner regime. Whether we look at absorption by the oxide or interferences, we need to have films in the order of hundreds of nanometers. So it concerns the Wagner regime. And the Wagner regime tells us that the thickness of the oxide grows as a parabolic growth. So that's to say that the thickness to the spread is proportional to the time. And here you have example of thin film growing on some, I think, I don't remember which metal, sorry. Maybe titanium after with time. And the most important fact is, of course, that this K factor here, proportionality constant, is very, very highly dependent on the temperature. It's RMS. So, ça marche. So, you will have different growth at different temperature, and of course, you will need to be much higher than the ambient temperature system. So, why is it interesting to do this with laser? Well, just for a simple fact that if you have nanosecond laser interaction, you will create high temperature at nanosecond scale time. If you look at what really happens, scales, from the classical gas kinetic theory, you can calculate the number of collisions of oxygen on the metal, and you will see that it's in this order, 10 to the power of 20. You can also calculate how many atoms are on the surface. Okay. So, for example, we are calculating incidentally for the studies. And at the end, you realize that you have 4.1 collisions per nanosecond per atom. So it means that the nanosecond scale is actually the ideal for precisely metals. So the very classical example here is, so why we want to grow a website? We need to make some structural colors. If I take a very simple configuration, I have oxide on a metal. And I have a wave color. So part of the wave will be reflected, so it's warning. And maybe the wave that is absorbed will make 2 full cycles inside the solar cell. When you make the sum of the 2 waves that are going out, so one reflected by the first surface and the one that's in the round trip inside the oxide, you will see a destructive interference. Same if you go for a wavelength, divided or multiplied by 2. So here, for example, this red light will come, make a full cycle, it's one trip, and create destructive interference. And obviously, there is a wavelength in the middle for which we will have a constructive interference. So if I look at the spectrum at the end, I had set white light, I will have more green reflected than blue of red. There is at this point. I could have also taken this green wavelength as destructive interference, and in this case, I would have a blue and red wavelength with a constructive interference. And I would have this spectrum, and I would obtain some kind of purple. Okay? A mixing of blue and red. So if I have a thickness in the order of wavelengths of my white light, I will have interferences and change in the respective spectrum. Obviously, all this works. Should be careful. The wavelengths that I use in the 2 cases are not the same. If I decide that my green is 550 nanometers, here my blue is in the UV, so it's So even when my red is in the infrared. Here, on the same regulation, just I added half the wavelength more, and a quarter of the wavelength more. The blue is at 440 and the red is at 7. So this is the way that people follow titanium. Titanium is a very good material to do this anodization, the growth, like some chemical process of oxide layer on titanium allows you to have all these nice colors. Thermal oxidation also allows to grow some more or less big TiO2, for example, here on nickel titanium alloy, and you will obtain for all the different conditions, very different. So we did this on titanium, and then we'll just pass it around the samples. So we have some small samples. Please don't open the box, which they have. Thanks. Okay. Because with titanium, if you go with a laser, you can precisely control the thickness of this oxide layer, and you will obtain all this range of colors. So the people that made these papers, they played around a lot, and obtain all this. This is only laser under the pigments, the colors, none of them. And this is almost non-iridescent. And you have all this range of colors, which I heard is not so bad. The only problem is that, as you saw this morning, there is a huge impact for metals of the direction from which you see the metal for the question of specular or non-observation. And if you don't, you're not careful, for example, here is non-specular viewing of this hamburger, and you will see that you lose a lot of light. So we played around. So these are the samples that you will see that were Sedao and observed by BOURQUARD, and you will see that we will observe all these colors. So this is for iridescent colors. So this is for this principle of interferences. Titanium. There are strong conditions to obtain this effect. Titanium is transparent, grows on oxide easily. It's a white pigment. But can we avoid iridescence here? It's not so easy to say. The reason is that titanium has a very high index. If you calculate the maximum angle of refraction of light in titanium is 27 degrees. So if I take my formula for interferences and I add here the angle of refraction, so it's here somewhere in the phase of this phase term. Well, sinus of 27 is not so lower than 1. So it's quite okay in the case of titanium. The small r has not much influence. And you will see it on the samples that will pass around. I really invite you to look with different samples. The color changes, but not much. So oxidation, it can also be made on other metals, like for example stainless steel. You can obtain a very large array of colors. So this is scanning speed versus power on stainless steel. And you see all the colors that can be obtained simply with a laser on metals. We did the same, then it's the same. And she will pass around, so 3 different stainless steel samples. Like one is just some kind of stainless, and you can see all the different colors that we obtain. You can even make a bit of color mixing. And so why does it work? Well, it's not interferences. It's more that we have an alloy with a lot of material available for oxidation. If I look at stainless steel, I can have, well, of course, I have chromium inside. The chromium oxide is green. I have iron oxide, which is red or black. I have nickel oxide, which is also green or black. Iron chromate, so some mixing with iron and chromium. Nickel chromate, which is yellow, and so on. Some people did the work of looking at 3 different sets of parameters to obtain yellow, blue, or purple, pink, let's say, steel. And with XPS, they obtain different process. So XPS is an X-ray trench spectroscopy technique. You send some electrons, I think, on the surface of the material. You collect some X-ray. It's the opposite. Yes. You send some X-ray on the material, and it will eject photons with some energy. And you can look at the energy of these electrons and come back to their state of bonding. But this is a bit of a complex technique, but what you can understand is that the different peaks come from different levels of oxidation. And using these techniques, they can go back to know which state, for example, chromium here or iron are oxidized. And they identified some spinels, so some oxides at different position, for which they identified some different ones. And by making here trading to predict from the contents and the color of the different components, they could obtain, they could calculate the color of their sample and see that it was corresponding to the experiment. So what they created was a mixing of different pigments, and that can allow to get angles. So here the spinel colors was very important. It is always oxide. So finally, if we take the example of copper, we can irradiate copper with a laser. We did it, so then we pass around the copper sample. And you will obtain different colors. So here our colleagues, they had a mix of nanostructures and colors, but they obtained this here very nice blue and even some green. The problem is that copper doesn't have any green outside. You might know that the statue of Liberty is green, it's made of copper. I don't know if you know why it's green. It's not copper oxide. It's carbon. You need carbon, yes. It's malachite or azurite, which has a mix of copper, oxygen, and carbon. Very important part, and even some water or OH group, which are green and blue. And so this carbon, it comes from our sample basically, or from what is in all the volatile organic compounds that are in that carbon. Okay, so I'm a bit late, so I will just skip these conclusions. That is a summary of what we saw. But here we have non-iridescent colors when we have pigment oxides. So that it really depends on the alloys that you have. Friends, available oxides. In some cases, oxides are not available. So the last question that we will try to answer with Sedao is, can we have other ways to have non-iridescent colors?
So the next case, which is plasmonic colors. Plasmonic, low plasmonics. Today we're just only going to talk about metallic nanoparticles and surface particles. And like plasmonic colors, that sounds quite scientific, but those plasmonic colors, they are not so exotic. In fact, they have been around 9 years. Pretty sure you have seen those tinted window glasses. And some of the colors, they just cannot be made by pigments. So it's plasmonic. There's embedded nanoparticles responsible for plasmonic resonance and the color light coupling. We have 2 examples there as well. We made in our tables. Well, this one is ourselves. It's from laser treatments of silver plates. And the other one is brochure is a ballpark radiated but not just like an ultra fast, ultra short laser pulses. And for plasmonic colors, metallic nanoparticles, there's surface plasmons. Surface plasmons is a saying of electron oscillations, and those metallic nanoparticles are used to launch surface plasmons. Depending on the characteristics of nanoparticles, it can launch different plasmonic nodes, and different plasmonic nodes and couple incident light, white light in different manners. and the coupling corresponds specific specific wavelengths of the white light. As a consequence, the surface guards a little bit of the resonance light, and what left over is reflected, and that's the perceived color. And as this schematic show, these kind of nanoparticles resonance in the blue, then what reflected the in the spectrum, visible spectrum, the red color as perceived reflected light. Then if you have these kind of nanoparticles which resonance the blue, then what reflected perceived to be blue. That's roughly how the things work. And to be more in details, we have this comparison of two different boxes, in which we have this is a macroscopic view, colors rendered by surface nanoparticles treated by lasers. For this case, and if we see the micro or nanoscopic wire, we have a medium-sized, there are many medium-sized nanoparticles. If you zoom in further, there are very few small-sized nanoparticles, and this is for blue, whereas for red, there are very few medium-sized nanoparticles, then you have a many more of small-sized nanoparticles. And this observation of what's happening afterwards is shown by this simulation. In the first case, this horizontal box, right envelope, you have just medium-sized nanoparticles, and our simulation indicates there's strong resonance at the blue lights at 390 nanometers. So you have and this is a coupling, and then the lights, the blue lights regarded at the surface because of the passwords. And then whereas in the other scenario where you have medium-sized nanoparticles, and you have a small-sized nanoparticles surrounded them, then you have two different resonance. You have it's a reduced blue resonance, and you have a enhanced, more pronounced red resonance in 680 to 15 nanometers. And this is to showcase the size of the nanoparticles. They play an important role in transmission. And then as well, there's another important thing is the interparticle distance. Well, if you want to have a blue, because the simulation shows you have an interparticle distance very small in the range of 10 nanometers. Then you have the resonance in the red. What left over for the reflection is blue. On the other hand, you have a long distances, like 100 nanometers, optical distances, for example, then you have the resonance in the blue. What left for reflection little of red. That's the first blue. So then the questions that are okay, that's nanoparticles. So what to do with our lasers? So actually, as well, we have the know-how of how to operate our lasers to control the size of the nanoparticles, as well as distribution interparticle distances. For example, the first one, our pulse duration, it is short or ultra short, change between 2 nanoseconds, to the size of the nanoparticles, and that's one. We can tune our laser doses as well, and change the distribution, interdistances, and the sizes. This is how we control our lasers, those different nanoparticles, or different plasmonic modes, and different plasmonic coverage on the surface. And so this is overall, this is a multiple all colors that we know here with our lasers. Plasmonic, we have the oxidation in terms of interference, in terms of pigments. We have periodic nanostructures for reflecting colors. So that's the first thing. Right now, I'm just isolate this. There's lasers to create structures. In this optical structural colors, I'm more interested in the sense we play with optical phenomena, reflection, absorption, diffraction, interference, and plasmonic resonance effects. By oxidation or by surface chemical reaction. And so towards the end, just once how to achieve targeted color, then first of all, we choose the less a laser with a red reaction. Then it's material, and that's why it's as a combination of the two, it's really useful. But we work together to find which types it's much more. And last but not least, on acknowledgements to everybody that contributes to this presentation. So thank you for the audience.